first 2 talks on mirror symmetry for cluster varieties.
Thanks so much for the invitation. It's great to be here. So I'm going to talk about some joint work with Mark Gross, Sean Keel, and Maxime Consage. So it's basically a story about mirror symmetry for cluster varieties, which are certain like rational variety. I'm going to explain that maybe the best way to think about a cluster variety is a special case of logical RBR variety. So this first talk, I think what I'll first do is say a little bit about what is a logical RBR variety, how we think about them, and a little bit about what mirror symmetry should look like for them. And the sort of big surprise for us was that mirror symmetry in the SYZ formulation was this scattering diagram at the base of the SYZ vibration, which is a really nasty thing. It's very, very difficult to control. And sort of one of the reasons we were able to make some headway with cluster varieties is sort of, for some reason, which I'll try to explain, the scattering diagram is more tractable in the case of a cluster variety. So I think what I'm going to do is, this lecture will be mostly just a background on logical RBR varieties and how to think about cluster varieties from a geometric point of view, and then the second lecture will be scattering diagrams for cluster varieties. So let me begin with the definition of a logical RBR variety. So I'll start with a smooth conditional variety Y, and D will be a normal crossing divisor Y. So locally looks like a union of coordinate hyperplanes. I'll write U for complement. And let's write n for the dimension. So we say that U is logical RBR. So if you're an algebraic geometry, you'd probably write K equals D is 0, or what's the same thing as a n form omega on U nowhere 0. So homomorphic volume form with simple poles along the boundary. There's also two conditions which we will almost always assume in these talks. So the first one is a positive assumption. So we say it's a positive logical RBR if the boundary supports an ample divide. Or what's the same thing? The interior is affine. Actually, we'll be able to sort of weaken this slightly. So you already saw examples in Elsa's talk where you have some logical RBR surface with some -2 curves in the interior. So that's not ample because, that's not affine because it contains some proper curves. We won't need to worry too much about that. So I can sort of slightly weaken this, say it's just say D defines a birational map, which is an isomorphism near the boundary. And the other condition is maximal boundary. So that's if there's a zero stratum divisor. So in other words, it's a point, divisor, which is an intersection of n branches. Bigger than usual. Okay, so let's see some examples. So the first example is just take a toric variety, and D being the toric boundary. So U is the torus. So that's an example of a one-column variety. And you know, the form is just dz1, dz1, which dz is, where these are the coordinates on the torus.
You don't need to assume Fano?
Sorry?
You don't need to assume it's Fano?
So I'm going to be following this point of view where you look at the open part and consider the wrapped category. So
Yeah, but this you assume it's Ky plus B is 0.
yes. So it's I mean it's still slightly weaker than Fano. See, I assume that D supports an ample divisor, but I don't assume that D itself. So you know some combination is ample, but these might not be all. What?
Oh, I see. But negative is not allowed.
Sorry?
Negative is not allowed. Negative.
I still
Yeah.
negative. Oh, all right. Yeah. More questions? So example 2 is, you know, so if I have a local Aviao, then I can construct more by blowing up centers. So I take Z inside D. So this is some codimension 2 subvariety of Y. Contained in a unique component. The boundary. So I don't want it to be a stratum of the boundary, inside a unique component. I just define Y tilde to be a blow. And D tilde to be the strict transform. Then this is again what's and so of course the simplest case is, you know, you have some surface, you just take a single point in the interior of one of the boundary divisors and blow it up. So it's a -1 curve, and I want to emphasize, so you know, the interior has changed here. So U tilde, you know, this E is not part of the boundary. So the interior of this variety has changed, you've got a new logical RBL. And I guess if, actually I don't know how you guys think about this, you might want to think about this as some sort of handle attachment. But yeah, so you know, so roughly speaking, I mean if you start with toric variety, at least up to homotopy, it's just the same as the compact torus, and what you're doing here is you're gluing on, again, just at level of homotopy, you're just gluing on a disk onto that torus. Of course, I should say immediately, you know, I said these two conditions, this will eventually destroy positivity if you do it too often. Right, so may destroy. And let me also remark, of course, you can also blow up strata of D. Just take some intersection of the divisors and blow it up. That's not and take, in that case, D tilde to be full inverse image. So interior hasn't changed. So we call this a toric blow-up. And so what I want to sort of explain is that we'll feel free whenever we want to perform toric blow-ups. They're not going to change the interior of the variety. We're only really interested in the variety U. So whenever it's convenient, we'll allow ourselves to do toric blow-ups. Okay, so then we have the notion of a toric model. So if I have a local Yao, many of our techniques work in the case where we have a toric model, and that's rather a central assumption. So what's the definition? So it's just a diagram. This, I start with my pair YD. I do some toric blow-ups. And then some of these non-toric contractions. To arrive finally at a toric variety. And so what I mean really, not just the toric variety, I want it to be the example one. So this is the toric variety and the divisor is the toric boundary. So the interior is really just a torus. Okay, and so let me just give one example of that. I can see why people were catching their fingers. So what's an example? So one example we've discussed already. Just take P2, and the divisor is going to be a line and a conic. So I'll decorate the curves by their self-intersection numbers. So I'd like to produce, this is my YD, I'd like to produce a toric model for this. Well, okay, let me first give you the answer. I don't want to spoil your fun, but I'm on a schedule here. So what you do, just let's blow up this point. So yeah, 3, 0, -1, and now I'm going to blow up this point. And now this looks suspiciously like the Hertzebruck surface, F2. So actually there's a -1 curve in the interior here, which can be contracted to give you toric surface F2. Oops, what am I doing here? I'm sorry. This was a -2. Okay. And if you didn't believe me about this -1 curve, you can sort of think, well, what does this -1 curve correspond to down here? It's just a tangent line to the conic. This is L, E bar. Okay, so this thing, of course, is not toric boundary, but it can be related to toric variety in this way. Everybody happy with the example? Okay. And so, it's a fairly easy lemma if you know about birational dispute surfaces. This is always possible in dimension 2. 1 CY2 with max boundary, then there is a toric model. So this point of view is new to you, but you're familiar with log Calabi-Yau surfaces. You might want to take your favorite example and find a story. Okay, but let's sort of give a cautionary example as well. This is certainly false in dimension 3. And it's sort of worse than you might expect. So log Calabi-Yau 3 can be irrational. So it's not even a rational variety in particular, there's no torus log. I was sort of debating why I was giving this example. I think it's mainly because it scares me slightly. So, this is something that, I should say actually, that this is something that we would not be able to treat by our techniques. But I believe what Mark's going to talk about tomorrow would apply to this example. So, so let's talk about it. So y inside P4 is a smooth quarter threefold. So it's a Fano variety, minus ky is over 1. And so then there's a result of Vygotsky and Manini in 1971 that y is irrational. I'm betraying my background in birational geometry here, so the origin, the way this is proved is just to show that the birational automorphisms of y is the same as its biholomorphic automorphisms. Of course, that's not true for a rational variety. There are loads of birational automorphisms. Okay, so what's my... Oops.
Did you tell us what D is in this case?
Yeah, I haven't said it yet. Yeah, so there's a sort of discussion about whether it's okay or not to use the boards at the end.
Yes, it is. Yes.
All right. So so what's the guy? So D is a hyperplane section. It's a section minus K. And I suppose it's probably true that y has to be special in moduli, but I'll just write down a specific example. So y is going to be f equals 0. F is this quartic. And so D is u equals 0. So these are the coordinates on my P4. So you see this has been cooked up so that if you set u equals 0, you just get the homogenization of the equation that Elsa was considering yesterday. So this boundary divisor has a cusp singularity. So this is irreducible. It has cusp singularity. Let's write down the affine equations. So if you remember what that looks like, there's some singularity. When you resolve, you get some cycle of... actually, I forget stuff in the sections here. Maybe it's -3. I don't know. You get some cycle of P1s as the exceptional divisor. So this is not my log Calabi-Yau quite yet, because I want it to be smooth with normal crossing. So what I'm claiming is, so it's easy to see, so there is a log CY resolution. So Y itself is already smooth, you just have to resolve the boundary. So this is now a normal crossing divisor. And detail that is just the inverse image of D. So the interior hasn't changed, it just changed how I've compacted it. Yeah, and so you see this might, I don't know, of course if you don't care about maximal boundary, this might seem a little weird. I was just sort of writing down some special D so it'd have a boundary of 0 strata. It'll work a little bit And let me just make a sort of remark to the notion of a toric model. It might seem a bit obscure, but roughly speaking, the existence of a toric model is approximately the same thing as there is a torus inside U. So this is the sort of thing that has been discussed several times already, that you can try to construct tori inside your variety by considering homological mirror symmetry and local systems on a Lagrangian on the mirror variety. So somehow this is something that's quite natural from the point of view of homological research. Okay, so let's talk a little bit about mirror symmetry.
Sorry, is this just roughly or?
Yeah. So I'm sort of sweeping all sorts of things under the rug. Basically, this will be something like birational geometry in higher dimensions. So the minimal model program, and there's all sorts of questions about singularities, what you do in k-dimension 2, flips and flops. I don't know how much you guys know, but anyway, of course here I just said I gave some very specific description in terms of blowing up smooth centers. That's not going to be true, but some sort of thing like that will be true away from k-dimension 2. So that's what I mean by roughly. Okay, so what is mirror symmetry going to look like for these guys? And here, you're the experts. I'm trying to say the right things, but let me give at least what I think is correct. So I've got some positive maximal Calabi-Yau. And what I want to next say is that I sort of expect mirror to be the same of the same type. Meaning, if I insist that U is positive and maximal log Calabi-Yau, then V, the mirror, whatever it is also of this form. In particular, so some of the examples that Elsa was discussing yesterday, on one hand, you had a log Calabi-Yau which did not have the positivity assumption, and the mirror was a Stein manifold. I want to avoid that situation. I want both sides to look roughly the same. But when I woke up this morning, I realized I know counterexamples to the statement. So let me just say that the counterexamples are rather stupid. The only examples I know, so let me just sort of explain what it is. So here's a counterexample. And you have to learn this by studying this cluster stuff. You take your favourite guy U, which is not positive. What you do is just pick an ample line bundle on U. Let's say L is ample on Y. Come back to the picture. And now you just pass to, just take the C star bundle given by the ample line bundle. Then that's basically the affine cone over U. So this is a positive Calabi-Yau. Tilde. Positive ones. But what's the mirror to this picture? So so whatever your mirror to U was, let's call it V. If you just sort of think about the duality of torus vibrations, the SYZ sort of heuristic, this C star bundle should correspond to a C star fibration on the mirror. Sorry, a fibration over C star. And so V is just some sort of arbitrarily nasty mirror, probably some sort of Stein manifold or something, and you're just sort of deforming that over C star. So this is, of course, not positive. So U tilde is positive, but V tilde is not. But what I was saying is, why is this kind of a stupid example? Well, there's this big group acting on U tilde. This is a torso, a C star. So somehow, it's not really a sort of primordial example. It's sort of. But anyway, I would be very interested if somebody has a sort of better answer about what's the condition to put on U for V to be positive.
Why is V tilde?
What I'm saying is, so U is just some arbitrarily negative guy. So like the sort of thing Elsa was considering, if you take P2 with a whole bunch of times, its mirror is some Stein manifold, like a Milnor fiber of a. And then this is just a deformation of that. So this is not even, I shouldn't even say positive, I mean, it's not even log cloud Yao, it's not even a variety. This is some Stein guy.
You expect it to actually be defined over all of C star?
No, I'm not. This discussion is not at that level yet. There's all sorts of convergence issues. Yeah. So let's not. But anyway, so I guess what I'm trying to say is that certainly in the examples that we've been thinking about, it is true that you have this property that if you start with a positive maximal guy, then its mirror is also the same. Oops. Okay, but anyway, let's sort of assume we're in this nice situation. So what's the sort of yoga here? So positive is going to imply there is a Liouville vector field X defined near the boundary. So I guess it's a slightly weaker setup than has been considered in previous talks. So I'm not assuming my variety is exact. I'm just assuming that I have this vector field near the boundary. So in other words, let me just write down the definition. I hope I'll get it right. So I've got this vector field. This equation, so omega locally near the boundary is exact, and x points out. And so then I want to say that I mean, again, this is a big question mark. People will probably complain that this is not actually written down, but at least expected that you can define the Raphri-Kai category in this context. So let me just also say the usual setup. Let's have a Kähler form and a B field. This is Raphri-Kai. Oh yeah, and I want to say one more thing. Again, I'd appreciate some help on this. This class. So this is an element in H2U. It should be in the image of H2Y. This is also the gradient piece of the weight filtration of the lowest gradient piece.
Sorry, what's the question mark?
The question mark. Oh, yeah, just saying. Well, good luck finding this in the literature. What I'm saying is, there's all sorts of convergence issues because I've not got an exact form here. But I think this is what is expected. Actually, I might be completely wrong, so you should talk to Denny and Mohammed and Paul. But okay. But anyway, so I'm just trying to state what we think is going to be the picture here. Yeah. So this was complexified case. Yeah, so this class in H2 Durham of U should come from Y, and this should also, if you're an algebraic geometry, is the same as the Picard. So the idea is that this is corresponding to, so the mirror is commutative. And so this is just something I learned from this very nice paper of Aru, Katsakov, and Orlov. In the case of Del Pezzo surfaces, this is a condition for the mirror to be commutative. I don't know exactly why that's true. If somebody can explain it to me, it'd be very quickly. Okay, so that's our A side. How did you get this book going? I'm not going to be able to get that back down. So, am I still doing what I think? Yeah, so let's try to write down conversions of mirror symmetry then in this context. So first of all, homological mirror symmetry. This category, the replica category, this should be equivalent to the derived category of coherent sheaves in a mirror. Again, so I'm doing this open version of mirror symmetry. And if we're in this nice situation, that both U and V are of this type we like, then presumably the converse is true as well. The replica category of V is isomorphic to, it is equivalent to the derived category of U. And let me just, the thing that sort of got us started on this in the first place was this consequence of this remark. So assuming this equivalence, if you look at the Hochschild cohomology of these two categories, so just HH0 in fact, then on the left-hand side you get the symplectic cohomology. Yes?
I mean, somehow there was a choice of an element of pick U on the left-hand side.
Yeah, that's just my Kähler form.
But somehow there was no corresponding choice at all on the right-hand side.
Well, I'm doing the usual thing, where so people split mirror symmetry into the A and B sides. So you consider category on one side,
That's sure, but I'm just saying that, I mean, as I vary B plus I omega, I don't expect the left-hand side to be unchanged.
Yes. Sorry, so the V varies in the complex.
So it's with respect to some divisor that's changing, or?
No. I'm sorry. I should have said this. I didn't write the dependence. Of course, V, the complex structure on V depends on the symplectic form on U.
Even though the divisor, but is that because the divisor itself is changing?
No.
So it's, in this case, let's just talk about that simple example I talked about before, where you have a toric variety and you blow up some points on the boundary. All you're doing is moving the positions of the points you blow up. In that case, so
Okay.
it's
It's just a mirror map, right?
Yes. Are we good? Yeah, please stop me, because I'm not sure, because obviously we're talking different languages sometimes. Okay, so to take Hochschild cohomology here, then the replica category, actually I don't know, I believe this is a theorem now, at least in maybe in the exact case, that the Hochschild cohomology is just the symplectic homology, symplectic cohomology, and here we know, just Hochschild Rosenberg theorem, it's easy. So this is just the global sections of the structure sheaf. And so under this assumption that V is affine, so if V is affine, so if we're in a positive case for V, then V is just recovered as the spec of symplectic cohomology. So this was kind of a, I don't know, when I first saw this I thought it was the coolest thing ever. You just write down this ring and then there's your mirror. And so as a corollary of this, which sort of algebraic geometers sort of got excited about, or at least I did, is that so the corollary of course is the basis, canonical basis of H0 of V, the coordinate ring, corresponding to a geometric basis in SH0. So these sort of resolvers. So I should say, of course, corollary of about three layers of conjectures. So the point is, this is again what we hope is true. And I want to just mention that James Pascal in Dimension 2 work this out carefully. You really do get the spaces.
I have a question.
Yeah.
So if you just define V like you've written, then there's no conjectures involved, right?
What's that say?
If you just say your definition of V is the other thing.
Oh yeah, yeah. So in our big paper, what we do is we say, I mean, I'll get to this later, but we say, okay, here's a cluster variety U. We define the mirror V to be this, and then we construct a basis of global functions on it.
No, there's still a conjecture. There's still a claim that the Radcliffe category is given by coherent sheaves on this.
I'm sure. Sorry, what I'm trying to say is that I think what Vivek was asking is that we have this long paper where we construct canonical bases for certain cluster algebras, and this is the heuristic. This is not the way we prove it, right? Yeah.
So, but how canonical is this variable?
Yeah, so that's something that I really recommend James's paper. I don't know. I hope it can be done in arbitrary dimensions, but you have to show the differential is 0, and then if you look at the boundary of your variety. I learned all this from Paul's paper. Bias view. You can write down these sort of candidates for the Rayburn bits.
It's the Bowman Sheridan elements.
Sorry, I lost you. I was talking to. Yeah, and so there's work to be done, but James explained it in dimension 2, and I would imagine you can do similar things in arbitrary dimension. Let's see. Where are we here? Oh yeah, so that was homological mirror symmetry, what we sort of expect, and let's talk about the SYZ version now. So first of all, we're looking for a Lagrangian torus vibration. So first I want to make a few general remarks that might be used to you guys. So well, first of all, I think everybody knows this. So what's the fiber class? So because we made this,
essentially the only thing that's conjectural is that in the wrap Fukaya categories you're interested in, the conjecture is somehow that there is a big enough abelian subcategory that generates.
I'm not making a conjecture like that.
There's no way that you can associate to a sheaf on a space a module over its Hochschild cohomology. It just uses a kind of coincidence in this case here.
So I'm just going to try and explain the SYZ approach now. So I take a 0 stratum of the boundary. So locally it's just looks like 0 inside the quadrant hyperplanes in Cn. What's my fiber class? Just the usual thing, just take this torus. I've heard it called the crossing torus. Just take this torus. This is the so that the class of that torus is the SYZ fiber. And so there's a obvious complaint of wait a minute. So you had to pick a 0 stratum, and then say bizarrely this was proved by Janos Gar. That 0 strata are linked by P1s. These are 1 strata. So actually, this is well defined. So all I'm saying is P1 in the boundary, 1 stratum. You've got your crossing tori here. You can imagine how it goes. You can sort of move it along this P1. See, these guys are homologous. This is actually a well-defined homology class. Okay. But let's sort of get more explicit about this. Let's actually try to write down vibration. Of course, I don't know how to do that in general, but in the case of a Platonic variety, it's been done. by Arun Abuzai Sakov. So of course in the toric case, we're just taking the equation by the compact torus. Moment map. And if it's a blow-up of toric, there's a way to modify the moment map. So I learned this from Symmetry, who you mentioned too. There's a very nice picture. So here's the image of the moment map. So I'm now looking at the moment map on the actual compact guy YD. So this flat space, this line corresponds to a component of the boundary. I'm just going to blow up a point of that component of the boundary. And how do I, what's the picture of the moment map? Just cut out this little triangle here. And then you glue these two edges together using an element of SL2Z, just a simple shear, to create the new base. So what you get is a so-called focus singularity, just ordinary singularity of the integral affine structure. On the family, over that you glue in an I1 fiber. So the monodromy is given by this matrix, and this line parallel to the boundary is the invariant direction. So that's torus vibration. Yeah, I'm sorry, you tilt, blow. So this is a picture in dimension 2, and in general, there's this paper of Arun Abuzai. I learned this from this nice paper of Symmetry. It's called 4 Dimensions from 2 in Symplectic Geometry. When you're in algebraic geometry and learning symplectic geometry, you go through all these remedial instructions from these expository phases. Actually quite fun. Okay, so that's our SYZ vibration. And of course, I should say the caveat that we're just constructing a Lagrangian vibration here. I'm not trying to do anything fancy like special Lagrangian or certainly not trying to find a root flat metric or anything like that. Okay. So then, with this, once you have this vibration, the mirror should then be constructed. Dual torus vibration, corrected by holomorphic discounts. So more about that later. Okay. I want to. I promised to tell you what cluster variety is, so let's do that now. Of course, it depends who you ask. If you were to ask me, this is what I would tell you. So, first of all, it's going to be a logical RBO, and secondly, it satisfies these conditions. So, there's a non-degenerate T-form. So it's actually sort of, if you want to say it, a log holomorphic symplectic. So with poles, log poles, along D. you know, if I wanted to be sort of careful about it, what I mean is it's in the wedge 2 of omega y. So as I mentioned before, you know, there's this notion of toric model. It's not completely universal, but this is assumed for cluster variety. So there is a toric model. And you know, again, as I said before, that's roughly the same as saying that there is an algebraic torus inside your guy U. Okay, and so now there's this fun exercise, which, I don't know, yeah, it's so trivial, but it's actually...
You really want non-degenerate?
Yeah, oh, I should say. So, of course, in the cluster world, they don't insist the form is non-degenerate. But it's almost exactly the same thing I was saying before, that you know, if it is degenerate, one of two things is happening. So, let's talk about the A cluster variety. In the A cluster variety case, there's a torus acting, just quotient by the torus, you get a guy which is non-degenerate. So somehow again, this is the key case. And then there's a sort of, again, there's the mirror dual picture where you're fibered over a torus, and what you actually have in the cluster case, you have a relative holomorphic two-form. I'm just looking at the fiber instead of the family.
The two, do you go up and then down, or?
Sorry.
The two, do you mean rational?
Oh yeah, the usual thing. So I sort of mentioned this thing before, that I really don't care if I want to do toric blurps, I do as many as I like. Okay, so here's the lemma. Actually, exercise. It's the following thing. So, okay, I have this toric model, and I want to say, well, how can I blow up in order that I get holomorphic two-form on the blow up? So, you know, so I have this guy. If I have sigma on U, I can sort of, you know, just take the corresponding holomorphic two-form on Y. So I get some guy sigma two-form on Y. Sorry, that's called sigma bar, the corresponding form on Y bar. So the blow-ups must be of the following form. So what do you do? So the center of the blow-up, the thingy blow-up, looks like this. Let me just write down some notation. So C intersect space here, chi equals lambda closure. So what's the, so where C is a component of D, you just choose some component of the boundary. Chi is a character of the torus. So here I'm just, just doing the completely naive thing. So I have my torus. Just look at the codimension 1 subtorus where this character is equal to a fixed value. So lambda still equal to C star. So is this some hypertorus? And then intersect with that boundary, you've already said. I haven't quite finished. So where? It's this board. So where? I want people to be able to do the exercise, so it's important you can see this board. So how do I tell you what the character is in terms of the divisor? So I take my form, omega. Sorry, sigma. That's a log 2 form. So what I can do is I can just take its residue along this divisor. That's now a log 1 form. that should be a d log of this character. So, actually, I don't know. I mean, of course, I'm not a symplectic geometry, but when you have a symplectic, it's a little bit like contact, sort of holomorphic contact geometry. Like holomorphic two-form restrict to a boundary divisor, you get this one form and this foliation. I want that to be algebraic, you know, given by this character. And I guess maybe maybe there's some. I'm sorry. So maybe there's some constant here. Okay. And so in particular, it's just the dimension 2 case. Cross a trivial n-2 direction. You see, so the dimension 2 case from, actually I should have said, I've defined a cluster variety. So, this was a real surprise to us, because we did all this work through the dimension 2 case, this nasty, huge paper, and then we realized that everything in dimension 2 is an instance of cluster. So this was a big surprise. I mean, I'm just saying because, of course, in dimension 2, omega is a holomorphic symplectic, and I already told you there's a toric model. Yeah, and so what I'm saying is this little lemma, which is really easy, is just saying that if you look at the blowups you're allowed to do, for each specific blowup, it's just the same picture you see in dimension 2 across a trivial direction. And so, just in dimension 2, you just had a boundary divisor, just blow up a point on that boundary divisor. Of course, that's not true globally, it's just true for each of the centers independently. So if you look at the actual picture of your toric variety, of course, the way these hypertori look in the boundary is something like this. They're not sort of all lined up. But you can imagine, so if you've ever seen a paper on cluster algebras, there's all this combinatorics that's just out of control. But the point is that if you understand this picture, I mean, it's really just a completely geometric thing that you can get your hands on. So if you're a geometer, this is really the way to think about it. Okay.
Sorry, so just to be sure, so all the mutation formulas and so on are contained in this statement and the lemma of it.
That's right, yeah.
Of this form.
Yeah, so let me try to explain more. Actually, when did I start? I believe I started a little bit late.
You have 10 minutes?
I do, very good. That's good.
7.
So what's the usual definition of a cluster variety? So what you say is, okay, so U is a union of tori with an atlas of tori. So I'm using torus in the way algebraic geometry uses it, so algebraic torus. And these are glued, so transition maps. Mutations given by this sort of formula. Oops, I'm sorry, this is of course a birational map, it's not a biregular map. So in inappropriate coordinates, it's given by this familiar formula. So of course, I mean, I'm sort of telling the whole story here. There's this huge tree of these tori, and the two adjacent vertices of the tree are related by a transformation of this form, and then of course, just take compositions. So what does this correspond to in our picture? It just corresponds to blowing up. Z, so this locus, of course, is just the locus. My divisor is Z2 equals 0, that's my boundary divisor. And then my character, I'm just intersecting with 1 is 0. Okay, but so let me explain in more detail. So And but this is something that's, again, is completely elementary if you know a little bit of algebraic geometry, or sort of algebraic geometry that everybody knows, not just algebraic geometers. So where does this transition come from? So let's just sort of draw a geometric picture. So what we have, so here's my divisor C, and here's my, I'm just going to draw a two-dimensional picture. Here's my codimension 2 locus Z, so it's really just literally exactly the two-dimensional picture across the trivial direction, so you don't lose anything. This is some P1 fibration. Yeah, so this is my hypertorus, this is a kite as well. Yeah, so in the two-dimensional case, I mean, you really don't lose them. Let's just think about two dimensions. So this is like a P1, and this is 0 curve, self-intersection 0. And then, as everybody knows, if you have a P1 bundle, it's something called an elementary transformation, right? Which is blow up Z. So this now becomes an exceptional curve, which is -1 curve, and a strict transform is also -1 curve. And this is all over this P1. And then you blow down, here we go. This is the blow. Z. And this is. Oops, sorry, what am I doing? And yeah, so this is your guy, your mutation. So in the notation we had before, I'm drawing a y bar. That's my toric model. I do some blow-ups to get y. So it's a single blow-up. I blow down the new toric model. I have these tori inside here. This is the interior of the torus T prime. And you can just see from this picture that the interior of y is the union of these two tori together with one extra point. Or in general, this could be codimension 2 locus. Let's call it W. So up to codimension 2, you're covered by these two tori. And so that's kind of what this story is talking about, that you get all these tori from these different toric models. Because the different toric models can be related in this way, you can see that they're given by these elementary transformations. I want to say something that I maybe didn't spend enough time on just then, is that I sort of assumed this hypertorus gives me a P1 fibration. Again, that's something that won't be true if you just start with the original by D. But as everybody knows, if you have toric variety, you want to produce a P1 fibration. That's just something that can be achieved by refining the fan. So, in the way to think about it, I have toric variety. There's some hyperplane in my fan, and I want that to be part of the fan. Then I get a P1 fibration. So this picture can be achieved after toric blows at the boundary.
Something you're saying I don't entirely understand is like the definition of cluster variety involves big union of lots of clusters.
Yeah.
Your definition over here, so that definition, not a the definition in codimension 2, it's just a definition. So how do you have some way of identifying that U?
So I should have said, yes, so maybe there's a slight lie in what I said, is that the thing that's union of tori is my thing minus some codimension 2 junk. And if you only care about regular functions, you don't care about codimension 2 in just the Hartog's topic. But there is that slight issue.
But whatever thing you define is certainly going to contain that one.
Yeah, right. So the cluster variety lives in our thing, and we've just sort of added. I mean, you probably wanted to add it anyway. It's sort of a bit daft to consider this surface and remove this point.
Well,
It's not really.
like this mirror symmetry statement at the beginning, EV depends a lot on, codimension 2.
Yeah. But actually, in Paul's notes,
include
Paul has these nice notes in his course. I forget the name of the course, but anyway, it's called a 4-dimensional example. And that point, that point better be in there, I believe, if I remember correctly. So I think we're right. So I'm kidding. But I hope it was clear as well. So the other thing was, I just did a finite number of blow-ups. So I'm only getting a finite number of tori immediately by this construction. But then you can do these elementary transformations, you can keep going, and that just corresponds exactly to changing.
So do you promise me I can fit this thing inside an algebraic variety?
What thing?
This big union of all of these U's.
Oh, so the question is this a well-defined thing? Yes. Yeah. Yes. I mean, there was some nasty, Mark did it all. Some nasty reference to Hartzell and EGA, etc. To how do you glue these infinitely many things together and make sure everything's kosher? But it does work. Yeah. So maybe I just recap very briefly and stop. So what I tried to describe is that you can write down this blow-up construction of a cluster variety. So you start with a toric variety, you do a finite number of blow-ups, you get this cluster variety. And in the cluster world, there's these infinitely many tori. If I take one toric model gives me one torus, but then there's this whole chain of whole infinite tree of different toric models related by these elementary transformations. That gives this cluster picture where you have infinitely many tori related by these simple transformations. So that's the geometric picture. And let me stop here and I'll continue.
Are there any further comments or questions?
I have a question about point 2 in your definition.
Oh yeah.
So could it be that you have one and the same variety with 2 inequivalent toric models in the sense that you cannot get from one to the other by mutation?
It's an interesting question. I know that Sean tried to get a graduate student to work on it today. He gave up. But the question, if you have a variety, can there be 2 inequivalent cluster structures? And it sort of seemed like the answer should be yes, but yeah, I don't know the answer. I think the answer there should be examples. I think.
Okay, let's thank Paul again and we'll resume at 4:15.